EPP, Module 5, Number 2. And the question was about giving the names of the compounds. Now I know you've got your homework back, so we'll just go ahead and this is a way to check yours, see how you did, to kind of check yourself. Obviously not a lot of discussion today. So the molecule NH4ClO2, the name for that is ammonium chlorite. Okay, ammonium chlorite. MnNO2 is, now, occasionally, what would you guys have for this? Manganese-2 nitrate, right. So manganese is one of those unique cases of transition that you're going to have to go through and figure out what its actual charge was. In this case, because it has the 2, means it ionizes to become a +2 metal. So, and the nitrate is a -1 polyatomic ion, so you need 2 of them to balance it out. So manganese-2 nitrate is MnNO2 sub 2.
Is it barium?
Well, it's Be, so it's beryllium.
Oh, beryllium.
Mm-hmm.
Beryllium 3-phosphate.
Just beryllium phosphate, because phosphate has a net, it has a 3 negative charge. So if I have 2 of them, that gives me a 6 negative that I need to balance out. Beryllium is a column 2 element. True? Yep.
Yes.
Way up on the top there. So it's column 2 element. So I need 3 at +2 to balance out 2 at -3. And then
Nickel phosphate.
and this is another one. More specifically, where are you going to find nickel at on the periodic table?
Nickel is, it's transition metal.
Transition, so we need to figure out what the charge is going to be, right? So since we're given the formula, we can then come up with a name. If you were just given nickel phosphate, you wouldn't know how to create the molecule, because nickel is a transition metal. But given that it's Ni1PO4-1, right, the phosphate, what must nickel be in order to balance out a single phosphate? Like, what is the charge of the phosphate polyatomic ion? One more, try again.
3.
3 negative, right. So phosphate's a 3 negative. We need 3 positive to balance it out, and we only have 1 atom to do that. So it's nickel 3 phosphate. Yeah. Yeah, so in each case, look at the metal. If it's column 1 through 8A, or, well, in this case, if it's a metal, it's column 1, 2, some of the 3s, 4, So look at the jagged line. Is it a metal? Is it a transition metal? If it's a transition metal, dig a little deeper to figure out what the Roman numeral has to be. If it's just a column 1A or 2A, boom, you can figure out what the charge is going to be. So the transitions, you've got to back engineer the charge. In this case, 1 polyatomic ion at 3 negative, this 1 nickel needs to ionize to balance it. Why it's 3 positive. All right. What does, and we pronounce it Vesper, but the acronym VSEPR stand for?
Valence shell electron pair repulsion.
Correct. Valence shell electron pair repulsion. So it's VSEPR, but it's pronounced Vesper because we do better with the vowel in that place. All right. So we're going to very quickly get to some geometries, but question 5, review question 5 says, explain Vesper theory in your own words.
It's a theory that states that molecules will create a shape and keep equidistant from the nucleus.
Keep equidistant from?
The nucleus.
Okay. What they're doing is they're pushing, not from the nucleus, but from each other. That's the key. So the way I wrote it was a molecular shape, or the geometry, will be based on the valence electrons of the central, or I call it the pivot atom sometimes, and the electrons being as far apart as possible. And they're going to be in pairs, whether that's a bond. Remember, a single bond, double bond, triple bond still has the same Vesper value in terms of geometries. But bonded pairs and unbonded pairs want to be as far apart as possible. And they're going to go to a place of equilibrium where their forces balance out. Remembering that an unbonded pair has a greater force pushing away than a bonded pair. Because think of it too, the unbonded pair is always around that atom. The bonded pair is occasionally away from that atom, right? So it's an average kind of a thing. So they're pushing away so that the forces are balanced. They're going to find a geometry where they reach equilibrium and they're going to stay there. Well, that's the way we understand it. That's the theory. Okay. 5.6 asks, why are the bond angles in a pyramidal smaller than the bond angles in a tetrahedral?
Because of the unbonded pair.
Right, that unbonded pair. See, pyramidal has an unbonded pair. Has unbonded pairs, but in a pyramidal it has one unbonded pair. Okay, but a tetrahedral doesn't. So since the pairs have a greater force of repulsion, pushing away, what that does is effectively squeeze the bonds together. And that creates a smaller angle of separation or bond angle. So good. All right. So for this homework, then we went on to practice problem 5.4. And these are a whole series of questions that say determine the shape of the molecule, give its bond angle, and draw a picture of it. So the first one here was the PCl3 molecule. Okay. So what shape did you end up with?
Pyramidal.
Okay, now I'm going to go ahead and say, well, two-dimensional Lewis structure, it's going to look something like this. Okay? We've got a column 5 element, an unbonded pair, and 3 chlorines. Now, my shorthand here, remember, I don't put the 1, 2, 3, 4, 5, 6 electrons around it, but they're there. Okay? I'm going to show the electrons around the pivot atom, the central atom, because that affects the geometry. The valence electrons around the exterior atoms doesn't affect the geometry. The bond affects the geometry. All right, so the pyramidal comes from this two-dimensional Lewis structure being brought into 3 dimensions. So when you get the pyramidal, what is the bond angle of a pyramidal?
107.
Right, 107 degrees. It's a trigonal pyramidal. Okay, and that's again because it would have been 109 had it been a pure tetrahedral. But the unbonded pair has a greater force of repulsion, a greater ability to squeeze those legs towards each other. And so it decreases the angle by 2 degrees. All right. 5.5, the molecule is H2.
Linear.
Linear, that's right. It's a homonuclear diatomic. Very simple, right? So the bond angle is 180 degrees. Yep. Okay. You're laughing because it's so simple?
Yeah.
Good. 5.6 is an SiCl4 molecule.
Tetrahedral.
Right. In 4 dimensions, it looks like this. I'm going to use a little X for the dot of the eye so we don't get it confused with an electron. It happens all the time. Okay, you're laughing, but it happens all the time. So when I'm doing geometries, I just write the X. And 4 chlorides, or 4 chlorines, singly bonded to the silicon, that creates the tetrahedral of 109 degrees. Right? You see you laughing, I'm kind of go, well, what's so funny?
The next one.
Oh, the next one. Okay. Well, let me turn the page. I've been working through all these last night, so as I see. An OF2, right? Is it an OF2 molecule?
No, I have CS.
Oh, you skipped one.
I did. Alright. You said OF2?
OF2, yeah.
The bent?
You did that really quickly. How'd you know? Yeah. Oxygen's column 6, fluorine's column 7. It needs 1. Oxygen's looking for 2. Boom, that's how it does. That's how it does it. And we create the bent molecule with 105 degrees. Very good. An 8 then, back to the one he was laughing about. Right, that's where we're at.
Yep.
Okay, CS?
Linear.
CS2 or CS?
I just have CS.
Just CS. Let me see. This is on. There we go. Right there. So triple bond, right? Now, the question on this one is determine the shape of the molecule and then give its bond angle and draw a picture of it. So here's the picture of it. It's pretty simple. Bond angle of 120 degrees. And then, since it's 5.3 and 5.8, I'm kind of combining the two because 5.8 goes back and says, okay, these questions 5.3 through 7, are they polar or nonpolar? I just kind of merge the questions. So with this geometry, Is the CS molecule polar or nonpolar? Polar, okay? We assume it's polar without looking up electronegativities. Now, I've said this in the past, but technically there are some molecules, or excuse me, some atoms that have the same electronegativities that are different places on the periodic table. They're not exactly the same, but then how exact do we want to get? How many significant figures are we going to look at it? So I may have misspoke before saying that technically I'm right, no two atoms have exactly the same electronegativity, but when it comes to how far we're going to take the sig figs, some of them do because of roundings. So, but what we can say is for C and S, they have differing electronegativities, right? Okay. So since there's only two of them, we don't necessarily have to figure out which one has a greater electronegativity. We can pretty quickly from the periodic table, right? Well, carbon is higher and sulfur is farther to the right, but we know that they're different. So if I ask you right now which one has a greater, you may not be able to judge the difference, but we know they're not the same. So one of these is going to be partial positive, and one of them is going to be partial negative, which means it is polar. Okay? This is determine the shape of the SiI4 molecule. Okay, so 2 dimensions looks like this, and then it forms a tetrahedral of 109. And the question then, and I know your question before was about polarities. So here for the molecule, it has polar bonds, 4 polar bonds, but is the molecule itself polar or nonpolar? Okay. Now, so now we're just looking at the molecule. The periodic table tells us that the difference between I and Si, there's a difference in electronegativities. We don't even have to know which one is more partial positive or negative, because we know, okay, we've got 4 polar bonds. The next question we're going to ask ourselves is about symmetry. Remember, the way we kind of rephrased it in here last class was, in order for it to be polar, this is a test for polarity. So is it polar? Does it have polar bonds? Yes, it met the first qualifier. The second one, is it asymmetrical? Is it asymmetrical? Which means, is it not symmetrical? So is this symmetrical? Yes, it is. So it's not polar. It's nonpolar. Okay, so that's kind of the way I think about it. We're not saying, is it symmetrical? We're saying, is it not symmetrical? That way we have a double yes. Otherwise, our rules would have to be, does it have polar bonds? Yes. Is it symmetrical? No. Then it's polar. And it kind of gives the yes, no, yes, no. If we make them both yes, does it have polar bonds? Yes. Is it asymmetrical? No. Then it doesn't work. Okay? So either way, you got to think a little bit. I just decided let's think of it in terms of asymmetry as opposed to symmetry. Here we've got 4 different bonds, but they're all perfectly equally symmetrical around the central pivot atom. Remember, if we have something that's based upon a tetrahedron, the only one that can possibly be nonpolar is a tetrahedral. And then only if all 4 bonds are exactly the same. So if it's based upon a tetrahedron and it's a trigonal pyramidal, or if it's a bent, it's polar. And if it's a tetrahedral and it doesn't have the same 4 elements connecting to it, it's polar. The only way it can be nonpolar, if it's based upon a tetrahedron, is if it is a tetrahedral with 4 identical bonds. Okay? Make sense? So if you say it's a pyramidal, it's polar. It's a bent, it's polar. It's a tetrahedral. Okay, are they all the same? Yes. It's nonpolar. Is any one of them different? Yes. It's polar. Trigonal. You know, and you get into the same kind of logic. Are there 3 bonds? Yes. Are they the same atoms? Yes. It's symmetrical, so it's nonpolar. We got about 5 minutes before the bell rings, so let's push on a little bit here. 5-5. We're not looking at Si4 anymore. We're looking at NF3. Okay, so lays out in 2 dimensions like this, in 3 dimensions as a trigonal pyramidal, 107-degree angle. Is it polar or nonpolar? It's polar. Why? It's based on a tetrahedron, but it's not a tetrahedral. It has to be polar. This unbonded pair is going to throw off the symmetry. Okay? For 6, the CCl2S molecule. What's its shape going to be?
Pyramidal.
Let's try again.
Trigonal.
Trigonal.
I have that written down.
See?
But I haven't gotten any of those right.
This is the 2-dimensional. Okay, so chlorine is picking up its 1 that it needs, so it has 8 and 8. Sulfur comes into it with 6. Carbon needs 4 more, and sulfur wants, well, and sulfur when they do the sharing, so it's 2, 4, 6, 8, and then everything else is satisfied. So that's what it looks like in 2 dimensions. We take that into 3 dimensions, and I told you put the central pivot atom here. We'll put the oddball on top, and then the 2 chlorines, so it's a trigonal planar molecule. Okay? But is it polar or nonpolar?
Polar.
It's polar. Why? It's a trigonal.
It's symmetrical.
So if it's symmetrical, that would lead us to think it's nonpolar, but what makes it polar?
Based off of the tetrahedral and it has polar.
No, it's not based off a tetrahedral. It's based off a trigonal. It's a 3-point, right? So our rule kind of changes. Now that I have 3 points, I have a possible for 3, and it makes 3, makes it trigonal. This would be symmetrical if, or this would be nonpolar if this were a chlorine, and it'd be perfectly symmetrical. But it's not symmetrical in the sense of this is a sulfur, not a chlorine. So there's a non-symmetry aspect to it. The bond angles are symmetrical, but the bond polarities are not. So the molecule is nonpolar. Or excuse me, the molecule is polar because it's not symmetrical. Remember, the statement is, does it have polar bonds? Yes. Are they asymmetrical? Yes, it's asymmetrical. It's not symmetrical. So yes, it's polar. This is a polar molecule. Next, number 7 is an Sf2 molecule. No. Fluorine is a column 7 element, right? It's only looking for 1 more. So 1 bond will satisfy the fluorines. Sulfur is column 6. So it's like an oxygen. Okay? So it's just like oxygen. It has 6. It needs 2. It has 2 fluorine. They each need 1, so that forms our bonds. So is this geometry going to be based upon a tetrahedron? Yes, it is. 1, 2, 3, 4 points of connection. It's based upon the tetrahedron. Is it a tetrahedral? No, because tetrahedral would have 4. All the points of connection would have a bond on them. So it's based upon a tetrahedron, but it's not a tetrahedral. Therefore, it is polar. Okay? Because it's 105-degree bent. Right? And as you look at this, you have a definite side over here with unbonded, right? And then you've got polar bonds on this side. So yes, is it polar? Well, do we have polar bonds? Yes. Is it asymmetrical? Yes, it's polar. Okay, we're on review questions, which means we've finished the second homework and we're pushing into the third homework, and we have about 30 seconds. Should we just stop here and wait for the alarm?
Yeah.
Yeah, because we can come back with review questions and press on from there as well. I'm going to go ahead and probably just leave everything recording, and I'll just edit out the center section there. So do you have any questions on, has this been helpful with in terms of polarity and nonpolarity? Just that little bit? Go ahead.
The thing when you have to do the plus sign and then the arrow,
Mm-hmm.
I don't understand which way the arrow goes.
Okay, we can talk about that till the alarm goes. So when you put the polarity indication symbol, that's the arrow with the plus sign, you look at the 2 atoms that are fighting for the electrons. They're bonded, they're sharing, but who's getting it more? Okay, so you look at the electronegativity based upon the periodic trend high and to the right. Which one has a higher electronegativity? The one that has the higher electronegativity is the one that's going to tend to have the electron. So we point the arrow towards the one with the higher electronegativity. Okay? Which means the other one automatically has the plus sign, the tail end of the arrow. Okay? So the higher electronegativity tends to have the electron, which means the other one tends not to have the electron, which means that that other one that tends not to have the electron tends to be partial positive, and the one that the arrow is pointing to tends to be partial negative. And that's it. All right? So that makes sense? So I didn't put all the polarity signs on these bonds, because a lot of them, when we're talking about polar and nonpolar molecules, it doesn't matter which way the direction is going, just recognizing that they're polar, one way or the other. And then you can determine the polarity of the molecule based upon the fact that it does or does not contain polar bonds. If you look at it and they're all nonpolar bonds, then it can't be polar. If there's at least one polar bond, now we've got to check for the second, the second qualifier. Is it asymmetrical? Remember, that means, is it not symmetrical? Yes, it's not symmetrical. It's like a double negative kind of a thing. Review question 7. What's the difference between polar and nonpolar covalent bonds?
Nonpolar covalent bonds in which the electrons are shared equally between the atoms involved, and polar is covalent bonds in which the electrons are shared unequally between the atoms involved.
Right. So they're covalent if they're shared. Ionic is they're given and taken, right? They're covalent if they're shared. Nonpolars are from equal sharing, and polar are from unequal sharing. That's the way I phrased it. But. All right. Review question 8 says, if two different atoms are bonded together with a nonpolar bond, what can we say about the electronegativities of the two atoms? Okay, so we've got two atoms that have a nonpolar bond. They're equally sharing. So just general statement about the electronegativities of them. Their electronegativities are, pardon?
The same.
Equal. Yeah. So they have the same electronegativities. If there's a nonpolar bond, they have an equal. Now before, again, I said, technically speaking, they would have to be a homonuclear diatomic, or they would have to be two atoms of the same element to be a perfectly nonpolar bond. But when you get to roundings and things like that, we do have different elements which are considered to be of the same electronegativity, because one might be higher and one might be lighter, and with that whole generalization. But so we can't say, technically, we can't say based upon that rounding that they're two atoms of the same element, but we can say that they have equal electronegativities. All right. Statement is made that oil and water don't mix, and it's a popular saying, say that the two people just can't get along. We say they're like oil and water. They can't mix. But why don't oil and water mix? Go for it.
Because one is polar and the other is nonpolar.
Okay. Oil is nonpolar, and water is polar. And likes dissolve likes. For right now, when you think of dissolving, thinking like they interact and they are attracted to one another. Dissolving is really about attraction, okay? And so likes attract likes, meaning polars will dissolve polars and ionics. Remember that, and ionics. Don't forget that caveat. Nonpolars only dissolve nonpolars. And we're going to actually do a lab on Monday that'll show that. What I'm going to do is take water and oil and try to mix salt and sugar in both of them. And so water is polar, and you would expect that the polar or ionic compound that's put into it would dissolve, and the nonpolar would not. And then conversely, with oil is nonpolar, and so you would expect that the nonpolar would dissolve and the polar would not. So, in any case. So 10, review question 10. Why does soap help wash away stains that water cannot wash away by itself?
Because the soap molecule, it has a water-attracted head, and its tail doesn't like water. And on a stain on your hand, the tail grabs a hold of the stain, but the water-attracted head, when the water runs over it, pulls it off, and pulls the stain off too.
Right. So the soap is long, it has an ionic end and a nonpolar covalent end. Right? And you're right that they actually need more explanation than just that, because the ionic end will be attracted to and act with and interact with the water, because it's polar and water is polar, and soaps tend to be nonpolar, or excuse me, stains tend to be nonpolar, and so the nonpolar tail, think of it this way, the nonpolar tail dissolves the stain and holds onto the stain. The ionic end gets dissolved by the water and is attracted to the water, and it ends up acting like a link that pulls the stain down the drain. Okay. Practice problem number 9, and also adding number 10 to it, because number 10 asks us to go back through all of these and say, do they dissolve in water? So rather than rehash every molecule again, I'm just going to combine these two questions. So is this an ionic, polar covalent, nonpolar covalent, and then based upon that answer, will it dissolve in water?
Nonpolar.
Okay. Magnesium is a,
Metal column 2.
and chlorine is a,
7.
that's right, nonmetal. So what kind of bond forms between a metal and a nonmetal? An ionic bond, right? This isn't a polar or nonpolar. This is an ionic bond. Okay? So then the second part is, will it dissolve in water? If it's ionic, will it dissolve in water?
No.
Well, is water polar or nonpolar?
Polar.
Try again.
Nonpolar.
Water is nonpolar, which means it dissolves. Oh, excuse me. You were right. I'm thinking backwards. Okay. Back up a second. Water is polar. Polars dissolve polars and ionics. Right? Because remember, poles are based on charges. Ionics are based on charges. So those that are based on charges dissolve those that are based on charges. Water is polar. This is ionic. Will it be dissolved? Yes, it will. It will be dissolved in water. Okay. B, the Sf2 molecule. Are there any metals here? Ask yourself that every time. Are there metals in this molecule? No. So it has to be some form of covalent bonding.
Polar covalent?
Well, right? No, I'm not saying you're wrong. Let's look at it. You said polar. Okay, this is our two-dimensional Lewis structure for the molecule. Goes into three-dimensional. It's a tetrahedral. Okay, it's based on a tetrahedron. It is a tetrahedral, so it still has the possibility of being nonpolar. But what about the bonds?
They're not all to the same. One of them's different.
Right. There's the carbon-chlorine bond is different than the carbon-fluorine bonds, right? So it meets the first category. It has polar bonds. Then you ask the second question, is it asymmetrical? Trigonal pyramidals and bents are always going to be asymmetrical. But this one, however, could be symmetrical, but it's not. Because even though it has bonds, the bond angles are all symmetric, the polarity of the bonds are not the same. Okay? So this has a different polarity in the bond than the others do, which makes this a polar molecule. And the polar molecule, will it dissolve in water? Yes, it will. I'm just checking I should have written yes. I did write yes. Okay. So yes, it will dissolve in water because water is polar. This is polar. Like dissolves like. The Cs2 molecule. Is there a metal? No. So there's some form of covalent bonding.
You say it's nonpolar.
Okay, let's just walk through the geometry, right? Carbon and sulfur, what will that look like? Okay.
Oh, it'd be linear.
Right, it's linear because sulfur is a column 6, it's looking for 2 more. Carbon has 4, it's looking for 4 more, and it ends up laying out like this. This is both the 2-dimensional and the 3-dimensional structure right here, okay? So the question for polarity is, first of all, does it have polar bonds? Yes. Electronegativities of sulfur and carbon are different, therefore there are 2 polar bonds here. Is there symmetry in those bonds? Yes, they're equal and opposites, they're pointing in different directions with the same magnitude. So the test for polarity, does it have polar bonds? Yes. Okay. Is it asymmetrical? No, therefore it's not polar, it's nonpolar. Okay, if it's nonpolar, it's nonpolar, will it dissolve in water? No, it will not dissolve in water. Because water is polar and it will dissolve polars and ionics. Okay. H2.
That is covalent, nonpolar.
Nonpolar covalent. Very simple, one of the simplest molecules you can have. The pull between the hydrogens are equal and opposite, right? This is, or first of all, this is a nonpolar bond, right? So knowing it's a nonpolar bond, the first test is, does it have polar bonds? No. It's not polar. I mean, excuse me, it's polar, right? Because it doesn't have nonpolar bonds. Will it dissolve in water? Okay, so again, what is it, polar or nonpolar? Nonpolar.
So it won't dissolve.
It will not dissolve. Correct. It will not dissolve in water. It will dissolve in other things. It'll dissolve in this case, it'll dissolve in a nonpolar substance, but it will not dissolve in a polar substance. Okay? SCCl4. Is there a metal? Try again.
Yeah. Can't find SC. Oh, it is. It's transition.
It's transition metal. It's a metal, which means this molecule is going to be, try again. It's got a metal and a nonmetal, meaning
Nonpolar.
it's ionic. Metals and nonmetals make ionics, right? You got to have all nonmetals to be covalent, either polar or nonpolar. So the first question is it ionic or covalent? The second question is, what form of covalent is it, if it's covalent? The third question then is the molecule polar and nonpolar? Fourth question is, based on that, will it dissolve in water? That's like the 4-step decision matrix you need to walk yourself through. So first thing, is this a polar or, excuse me, is this a covalent or an ionic molecule?
Ionic.
Will it dissolve in water?
Yes.
Yes, it will. Because water is polar and it dissolves polars and ionics. So yes, it will dissolve this molecule. Okay? Is it making sense? I mean, even if you get it wrong, is it making sense?
Than it was.
Okay, that's good. A lot better than it was. I'll take that. A PCl3 molecule. Are there any metals in this? No. So it's some form of covalent, right? Is it polar or nonpolar covalent? We need to know the geometry first. Okay, column 5, good. So column 5s tend to form what form? What geometry? Column 5s tend to form this, right? They tend to form trigonal pyramidals because they have an unbonded pair already. So they tend to form this, especially when they're all single bonds. So when you've got a column 5 and a column 7, it's going to be, and they're all column 7s, it's going to be a trigonal pyramidal. So that's the 2-dimensional, that falls into the 3-dimensional 107. Is it polar or nonpolar? It's nonpolar, or excuse me, it's polar. It's a polar molecule because, right, even though all 3 of the bonds are of equal value, they're not, the molecule itself is asymmetrical. It's polar because it has polar bonds and it is asymmetrical. The asymmetry comes because this is not a chlorine bond. It's something other. So remember, if it's based upon a tetrahedron and it's not a tetrahedral, it can't be nonpolar. It is polar. Will that dissolve in water? Yes, it will. Because it's polar and water is polar, likes dissolve likes. Extra practice problems. I think it's kind of like continuation of the same thing, right? We're looking at SiFCl3. Is this helpful, guys?
Yes.
Okay. So classify each of the following as ionic, polar, or nonpolar, and will it dissolve? Exact same question. On the SiFCl2 molecule, first of all, does it have a metal in it?
No.
No. So it's some form of polar, some form of covalent. What's the geometry here?
It's polar.
What's its shape? What's its geometry?
It'll be a tetrahedral.
It'll be a tetrahedral. Good. Si, silicon, is a column 4A element, and we have 4 other atoms involved, so it's very quickly, you can see that it looks something like this, which in 2 dimensions turns into a tetrahedral in 3 dimensions. So in terms of its shape, it's symmetrical. In terms of its bonds, are the bonds symmetrical? No. We have polar bonds, right? So the test for polarity, is it polar? It's polar if it has polar bonds, good. It's polar if it's asymmetrical. Is it asymmetrical? Yes, it is. It's asymmetrical because that fluorine's not a chlorine. If that was a chlorine, it would be symmetrical. So since it's asymmetrical with polar bonds, this is a polar molecule, and it will dissolve in water. Sf2. Somebody throw a venture out there?
It's a non-metal, so it's going to be covalent. And would it be polar?
Okay, so I agree with you. It's some form of covalent because there's no metal involved. What is the geometry going to be?
Linear?
Okay, so we've got a linear, and this is its 2 and 3-dimensional. Does it have polar bonds? Yes, it does. Is it asymmetrical? No, it's not asymmetrical, therefore it is nonpolar. Okay? It would be polar if the symmetry was off, but it's not. There is symmetry there. So polar bonds, but unfortunately it's not asymmetrical, therefore it fails the test for polarity, it's nonpolar. So this is a nonpolar molecule. Will it dissolve in water? No, it won't. Because water is polar, likes dissolve likes. Water dissolves polars and ionics. All right. Aluminum trifluoride. Is that what it's called? Is it aluminum trifluoride? No, it's just aluminum fluoride because it's ionic. Good, it's a metal and non-metal, it's ionic. So we don't have to worry about the bonds, there's no diagram, it's ionic. Okay? Since it's ionic, will water dissolve it? Yes. Yes, it will. Nitrogen.
Covalent, and that would be
It's a homonuclear diatomic, right? So it only involves 2 atoms. Every covalent bond with 2 atoms is, well, every one is linear, right? If it only has 2 atoms, it has to be linear. We've got 2 nitrogens. So the 2 nitrogens are forming this linear triple bond. It's homonuclear diatomic. So is the bond polar or nonpolar? It's a nonpolar bond. So the molecule has to be nonpolar. Will water dissolve it? No. Carbon tetrachloride.
That is most definitely a polar bond.
Okay, you said a polar bond. Okay, I'll agree with actually 4 polar bonds, right? It's 2 nonmetals, which means it's covalent in some form. It's a column 4A element and 4 column 7A elements, which means it's going to form a nice, perfect 2-dimensional, then 3-dimensional tetrahedral. Now I'll do the tests for polarity, for being polar. The test for polar is, does it have polar bonds? Yes. Is it asymmetrical? No. Therefore it is nonpolar. It failed the test for polar. So it's nonpolar. Remember, if it's based on a tetrahedron, it has to be a tetrahedral. And if it's a tetrahedral, it has to be 4 identical bonds. Do we have that? Yes, we do. So it's nonpolar. Will it dissolve in water? No, it will not. The Sf2 molecule. Is it ionic or covalent? Covalent. Okay. What column is phosphorus in?
7.
Phosphorus? P?
Oh, 5.
5. You just did one earlier. Column 5 and 3 column 7s.
That's a pyramid.
Yeah. So it comes out to be a trigonal pyramidal with 107 degrees. Is it polar or nonpolar? Try again. Polar. Polar, why? Why is it polar? Just wait till the bell. Why is it?
Because it's asymmetrical.
It's asymmetrical. It was based on a tetrahedron. It's not a tetrahedral. It has to be nonpolar. Or excuse me, I just said it wrong. It's based on a tetrahedron. It's not a tetrahedral, therefore it has to be polar. If it were a tetrahedral, it might be nonpolar if all 4 bonds are the same. And that's it.